Training the largest neural networks often hits an invisible wall, not speed but memory. What if you could train models with hundreds of billions of parameters using significantly less GPU memory than even smaller ones, without prohibitive slowdowns? This isn't just about throwing more hardware at the problem, it's about a technique called gradient checkpointing. Standard backpropagation demands storing every intermediate activation from the forward pass, so gradients can be precisely calculated later. For deep wide networks, these stored activations consume vast amounts of VRAM, quickly exhausting even high-end GPUs. Gradient checkpointing addresses this by recomputing those activations on demand, rather than storing them all. During the forward pass, only a select few intermediate points, checkpoints, are saved. When backpropagation needs an activation not directly stored, the relevant segment of the forward pass is simply rerun from the last checkpoint. In PyTorch, you implement this with torch utils checkpoint. You wrap specific layers or blocks of your model with this function, for example, a series of NN transformer encoder layer modules. PyTorch then intelligently manages the recomputation for those wrapped segments, reducing the peak memory footprint dramatically. The trade-off is a slight increase in training time, typically a 2050 slowdown, because some forward pass computations are duplicated, but for models that wouldn't fit in memory otherwise, it's an absolute game-changer. Consider fine-tuning a 7 billion parameter large language model, or training a massive vision transformer for high-resolution medical image analysis, like detecting early-stage cancers from gigapixel pathology scans. Gradient checkpointing often makes these tasks feasible on more accessible hardware, or enables truly unprecedented model scales on state-of-the-art systems. Traditional approaches would force smaller batch sizes, which can harm training stability, or demand prohibitively expensive multi-GPU setups with complex parallelism, while mixed precision training saves memory by reducing data types. Gradient checkpointing directly tackles the activation storage problem, and they can even be combined for maximum effect. As AI models continue their exponential growth, memory optimization techniques like this are becoming not just an advantage, but a necessity. It pushes the boundaries of what's trainable, democratizing access to massive model research and deployment. Ultimately, gradient checkpointing reframes our perception of hardware limitations. It demonstrates how clever algorithmic design, implemented elegantly in Python libraries like PyTorch, can unlock the next generation of truly transformative AI capabilities, built on models previously deemed untrainable.